In the previous video, we saw this theorem which gives us a necessary and sufficient condition for two integers a and b to be relatively prime, at least one of which is non-zero. We saw corollary 1 to this theorem and we started proving corollary 2, but we were unable to finish it. So let's just do that now. So in this corollary, a, b and c are three integers. It is given that a and b both divide c and also a and b are relatively prime. We have to prove that their product ab also divides c. So we start the proof by first using the definitions of these divisibility relations. Since a divides c and b divides c, we have c equal to au and at the same time c is equal to bv for some integers u and v. So here we have just used the definition of divisibility, that's all. Now additionally we are given that a and b are relatively prime. Since GCD of a and b is 1, so now we can use theorem 2.4. By theorem 2.4, there exist integers x and y such that 1 is equal to ax plus by. Then c can be written as c times 1, so that becomes c times ax plus by, which is cax plus cby. Now in this sum, in the first term, we can replace c with bv, so it will become bvax, and in the second term we can replace c with au, so the second term will become auby, and we can take ab common out. So it will be ab times vx plus uy. Now because x, y, u, v, these are all integers, vx plus uy is also an integer. So this implies ab divides c, and that completes the proof. After this we have a theorem. Theorem 2.5. Actually it is named after Euclid and it is named Euclid's lemma, but it is very important, so it has been stated as a theorem. And the statement is this: if A divides the product BC with A and B relatively prime, that is GCD of A and B 1, then A divides C, then A has to divide the other integer C. with which it is not relatively prime. I mean, nothing has been said about whether a and c are relatively prime or not. A, b and c are just some integers, and it's given that a divides the product bc and a is relatively prime with b, then a has to divide c. That is Euclid's lemma. Again, since it's given that GCD of a and b is 1, so we can use theorem 2.4, since this is equal to 1, by theorem 2.4, there exist integers x and y such that 1 is equal to ax plus by. Now if you multiply both sides of this equation by the integer c, you will have c equal to scx plus bcy. Since a divides ac, a obviously divides ac because ac is a multiple of a, and that is because c is an ac is an integer multiple of a, because c itself is an integer, and a divides bc. This one is given to us in the hypothesis. So because of these two divisibility relations, we will have this. So a will divide scx plus bcy, or a will divide c, because that's what c is, and that just proves Euclid's lemma. Now the condition in Euclid's lemma that a and b have to be relatively prime is necessary for this lemma to work. If you lift this condition, if you don't assume it, then this would not necessarily imply this. If a and b are not relatively prime, then the conclusion of Euclid's lemma may not hold. It may be false. For example, 12 divides 8 times 9. Take 12 in place of A, 8 in place of B, and 9 in place of C. 12 definitely divides 8 times 9, which is 72, but 12 neither divides 8 nor divides 9. You can easily see why these are these non-divisibilities are true because both 8 and 9 are less than 12. However, 72 is divisible, 72 is divisible by 12, yes, or 12 divides 72. And note one more thing, that here actually this condition is not true no matter what you take as b here. If you take b equal to 8 and 12, because our a is now 12, 8 and 12 are not relatively prime, their GCD is not 1. Similarly, the GCD of 9 and 12 is not also 1. So these two are also not relatively prime. And you see that the conclusion of Euclid's lemma in this case is false. It's not true. Okay, now finally there is one more theorem which will complete this section. And before we state the theorem, there are some remarks by the author, and the remarks are this: the subsequent theorem that means the one we will see now is often used as definition. Is often used, or the author writes, theorem often serves as a definition, same meaning. Used as a definition of GCD of a and b, where of course a and b are two integers, not both 0. But what is the reason for this? There is an advantage. The advantage of using it as a definition is that the order relationship is not involved. And that is why thus it may be used in algebraic systems which have no order relation. We will see what these sentences mean actually. Now, before we see what these things mean, let's just see the statement of the theorem. This is the last result of this section. Let a comma b be integers. Not both 0. at least one of them is non-zero. For a positive integer d, d is equal to the greatest common divisor of a and b if and only if the following conditions are true. That is, two conditions are given: d divides a and d divides b, and condition b, if c is an integer that divides both a and b, whenever c divides a and c divides b, then c divides d. Okay. So what we are asserting in this theorem is that if these two conditions are true, then such a positive integer d will be equal to the greatest common divisor of a and b, and conversely the greatest common divisor of a and b satisfy these two conditions. That means these conditions themselves can be taken and we can say that the greatest common divisor of a and b is a positive integer such that these two conditions are true. It can now be used as an alternative definition of GCD of a and b. And let us also recall the original definition of the greatest common divisor. For two integers a and b, a positive integer, say for the time being let's take that as say e. For two integers a and b, a positive integer okay, e is said to be a greatest common, or rather here I should not say a greatest common divisor but the greatest common divisor of a and b if the following conditions are true. The first condition is this: e divides a and e divides b, which is exactly the same that we have here. And the second condition says this: whenever c divides a and c divides b, where c is of course some integer, then c is less than or equal to e. This is the original definition of the GCD of a and b. Then we will say that e is the GCD of a and b. Now you can see that this definition is literally the definition of the greatest common divisor. How? The first condition tells you that e has to be a common divisor of a and b. E has to divide both a and b. E is common to the sets of divisors of a and b. And the second condition tells you that it's the greatest such common divisor. If c is any common divisor of a and b, then c must be less than or equal to e. That means e is the largest among all common divisors of a and b. And that is just the straightforward definition of the GCD, or the greatest common divisor of two integers a and b. Now in this theorem, condition a is just the same as condition 1 in the original definition of GCD, but condition b is different. Is not like this one. It starts similarly, but then the conclusion is something else. Here we are saying, if you just simply used, for the sake of comparison, if you used D here, then you get this condition B. Okay, whereas here here you get condition 2, whereas in condition B the conclusion is C has to divide D. Here the conclusion is C must be less than or equal to D. Okay, now what we are saying here is this: the advantage of using this as the definition, which we can use, not that we can use this as the definition of GCD, because these two conditions together are equivalent to these two conditions together. So if some D is satisfying these two conditions, then that D will also satisfy this, and the converse is also true. So that means these two conditions are equivalent to these two conditions. So we can use this instead as our definition of GCD. Now if we do, what is the advantage? The advantage of using it as definition is that order relationship is not involved. In this definition, this ordered relationship that we have in the system of integers, which allows us to say things like this integer is less than that integer or greater than or equal to that integer, that thing is not available here. Here we need only divisibility. Thus it may be used in algebraic systems having no ordered relation. Now the algebraic system that we are working in is the system of integers, which has the set of integers, the operation addition, the operation multiplication, and the ordered relation. This part, however, is not always available. There are other algebraic systems also. If you have studied abstract algebra, you would know that similar systems are there, many different types of systems which behave like the system of integers, or at least this part of the system of integers, and they are called rings. Among rings, there are special types of rings which are called Euclidean rings. In Euclidean rings also we have a notion of greatest common divisor of two ring elements. See, that's why at one point I started saying a greatest common divisor. That's because in a general Euclidean ring, greatest common divisor, the way it is defined like this, is not unique. However, two greatest common divisors are related in a very nice way. That's not the point here. The point here is that in a general Euclidean ring, it may not make sense to say that this ring element is less than that ring element. Such an ordering of the ring elements may not be available. But there you can continue to use this definition, because this does not involve order. It only involves divisibility, which however is there in any Euclidean ring. So that's what the author is saying here. That's why this alternative definition is important, and it allows us to define a similar concept of GCD for Euclidean rings, in spite of the fact that many Euclidean rings may not have any notion of less than or equal to. Let us now prove this. If you find these remarks that I have made now going over your head, and you find these things unfamiliar, suddenly rings, Euclidean rings. If these terms are unfamiliar to you, just don't bother. Just know this much, that besides the system of integers, there are other similar systems also where we can investigate similar things, like what we are doing here in number theory. Some such number theoretic investigations can be carried out in other algebraic systems. For that, this definition is needed. Only that much is enough. Okay, so let us now see the proof. So we need to prove two things. First of all, if D is the greatest common divisor of A and B according to our original definition, then these two conditions are true and the converse. So let's prove this first. First, assume that D is the ordinary GCD of A and B. Then by definition, that means this definition, D divides A and D divides B. So that means we need to show these two things. The first one is already true and it comes directly from the definition. In fact, it's a part of the definition. Also, we know, okay, now what I'm going to write here is a result that we have seen. Which result I don't remember right now. You go back to the previous video, you see which theorem or lemma or whatever it is that we will be using here, you put that name here. Also, we know that it's the main result about the greatest common divisor, which says that for any two integers, at least one of which is non-zero, there exists a GCD, and the important part is that the GCD is a linear combination of the two integers. So D, being the GCD of A and B, can be written like this. For some integers x and y. Now if C divides A and C divides B, if C is an integer that divides both A and B, then C automatically divides AX plus BY, that is C divides D. So condition B is also true. That means our ordinary greatest common divisor of two integers, they satisfy these two conditions. Now conversely, assume that D is a, this is gone, okay, we have proved this half of the theorem, and now D is something again new. Newly we are considering D, that D is a positive integer, but this time D satisfies conditions A and B. Our aim is now to prove that this D will be the GCD of A and B. For that we need to show that 1 and 2 are true. 1 is already true because condition 1 is nothing but condition A. We need to prove that 2 is true from condition A. We have this and D divides B. Let C be an integer and C divides B. Our aim now is to prove that C is less than or equal to D. Since C already divides something, so C cannot be equal to 0. So as an integer, C is either a negative integer or a positive integer. Has C been restricted to be a positive integer in this lemma? No, nothing is told about the sign of C. So C may be negative also. If C is less than 0, then we obviously have C less than or equal to D, and in fact we have C strictly less than D. That is because D is positive. D is a positive integer, and if C is negative, it has to be less than D. Now assume that C is positive. Now because condition B is satisfied by D and C divides A and B, so we have this. By condition B, we have this. Okay, since both C and D are positive integers, this implies, that means this divisibility implies C has to be less than or equal to D. And where is this inequality? I am trying to say how this inequality appears from this divisibility. That is, let us just see that also. Because C divides D, so D will be equal to C times E for some integer E. That's what divisibility means. Now note that D is a positive integer, C is also a positive integer. So E, first of all, E cannot be of course 0 because D is positive. Also because additionally C is positive, E cannot be negative also. So that means E has to be a positive integer. And because E is a positive integer, E is greater than or equal to 1. Now multiply on both sides by C, you will get CE greater than or equal to C. And note that the inequality has not got reversed because C is positive. So that's how you get D greater than or equal to C. But now see what we have ultimately got. For us, now two things are true. D divides, D is a positive integer which divides both A and B, and whenever C is any integer that divides both A and B, C must be less than or equal to D. So according to our original definition of GCD, D is the GCD of A and B. This completes the proof, and it also completes this section. Let us now go to the exercises. So the first few will be very easy, nevertheless we will solve them. If A divides B, show that minus A also divides B, A divides minus B, and minus A divides minus B. Since A divides B, we have B equal to AC for some integer C. Now to conclude these divisibility relations, we modify this equation B equal to SC. Note that, okay, so in the first one we have been asked to show that minus A also divides B. So B can be written as, because B is SC, you can also write this as minus A times minus C. Just like C is an integer, minus C is also an integer. Just like that, minus B can be written as A times minus C. Multiply both sides of this equation by minus 1, you will get this. And also minus B can be written as minus A times C. From the first equation here, this one, we get this relation, minus A divides B. From the second one, we get this one, A divides minus B. And from the third one, we get this, minus A divides minus B. Then exercise 2, it has some parts. Given integers A, B, C and D, verify the following. Part A. If A divides B, then A divides BC. Part B. If A divides B and A divides C, then A square divides BC. Okay. Part C. A divides B if and only if AC divides BC, where C is any non-zero, where C is non-zero. D. If A divides B and C divides D, then AC divides BD. These are also rather easy, just like the previous one. Anyway, let's go through each one of them. A. If A divides B, then now in translating this divisibility relation into an equation, don't suddenly write B equal to AC, because the integers A, B, C and D have already been taken. So take something else. Say B equal to AE. For some integer E. So we have to prove that A divides BC. So BC can be written as A times BE. Now just like E is an integer, BE is also an integer. So this implies A divides BC. That's part A. Then part B. If A divides both B and C, then A square will divide BC. I think it will rain again. I don't know if you are able to hear the thunder. It rained an hour ago. Again, I think it will rain. The rainy season has started. Anyway, moving on. If A divides B and A divides C, then B is equal to AU and C is equal to AV for some integers U and V. Now BC, if you multiply these two equations together, you will get BC equal to A square times UV. UV is an integer, so this implies A square divides BC. You may have noticed one thing. we are no longer saying things like in this divisibility relation A has to be non-zero. Those things are already there in the background. Okay, you can see one thing here. Because A is an integer that divides B and C, again A has to be a non-zero integer, because we don't have any concept of divisibility by zero. Such a thing is not there. So A has to be a non-zero integer. Now because A is non-zero, A square is also non-zero. So from this equation it makes sense to write this relation, although we won't mention that explicitly. Okay, such things are understood. Then part C, A divides, so this is an if and only if statement. This implies this and also this implies this. So that means we have to prove two things. Firstly, you assume that A divides B. Then B is equal to AU for some integer U. So BC is equal to ACU. Which implies AC divides BC. Do you see that thing here that I was mentioning just now? It's given that C is non-zero, that's why AC is non-zero. Non-zeroness of A is coming from here. In this relation it's assumed that A is non-zero, and additionally it's given that C is non-zero. So that's why AC is non-zero, and it makes sense to say that AC divides BC. Just to emphasize the fact, we write here in brackets, note that C is non-zero. Okay, so that is one half. Next, assume this. For this part, however, you don't need to additionally assume that C is non-zero, because in this divisibility relation AC must be non-zero, so automatically C has to be non-zero, and also A has to be non-zero. Then BC is equal to AC, say V, for some integer phi. Now invoke the non-zeroness of C. Since C is non-zero, from this equation you can cancel C from both sides, loosely speaking. Since C is non-zero, we have, so doing that you get B equal to AV. Now because A is also non-zero, from this equation we can write A divides B. Okay, just give me a moment. Okay, so non-zeroness of A will now allow us to write from this equation this divisibility relation, that A divides B. So A divides B if and only if AC divides BC, where C is non-zero. So that is part C. And finally in part D, we have these two things. If A divides B and C divides D, then we need to show that AC divides BC. Yeah, the power is gone because of the lightning. Then B is equal to, say, AS and T is equal to CT for some integers S and T. Thus, now if we multiply these two equations together, or if you calculate BT using these expressions, you will see that it's equal to AC times ST. Now, these two relations imply A and C have to be non-zero. So AC is non-zero and S and T are integers, so the product ST is also an integer. So from this equation, you can write that AC divides BT. That's what we had to prove. So this completes the solution. So you see that although the statements or the individual parts look extremely easy, and they are easy, but these little things have to be taken care of, namely non-zeroness of the divisor. Then 3, prove or disprove. Okay, so this is an open-ended exercise. If whatever is said here is true, we have to prove it. Otherwise, we have to disprove it by providing some counter example, which shows that the statement is not true. If A divides B plus C, where A, B and C are of course integers, then either A divides B or A divides C. No, this is not true. Is not true because, for example, you can take take a very easy example by taking any A and taking B equal to minus C, such that B is not divisible by A. However, if you don't want to take negative integers, you can take this one also. 2 divides 1 plus 1, but 2 does not divide 1. So A divides B plus C, but A does not divide B and A does not divide C. Here B and C are the same thing, they are 1. So that means the given statement is false. And if you have a little confusion about truth of such a statement where you have variables, then just know that a statement like this is said to be true if whenever for all the this particular statement is an if-then statement or an implication which has two parts, right? This is the hypothesis, and after then whatever you have, that is the conclusion. But in general I am saying, if you have a mathematical statement which involves variables, generally when we are asked to prove such a statement, it means that we are assuming that for all the possible values of the variables the statement is true. You may, for example, here it is actually not a single statement, it is infinitely many statements. You change the values of a, b and c. There are infinitely many choices for each of a, b and c. That will generate infinitely many statements. The moment we are saying that something like this is true, we mean that it is true for all possible choices. That is not true, because this particular choice has shown us that that is not the case. Maybe for some choices it will be true. You can take a equal to 2 here, b equal to 4 here and c equal to 4 here, then this statement will be true. That particular case will be true. Okay. Now next, exercise 4. For n greater than or equal to 1, where n of course is an integer, use mathematical induction to establish each of the following divisibility statements. So there are some parts now. 8 divides 5 to the power 2n plus 7. 8 always divides such numbers no matter what n is. 15 divides 2 to the power 4n minus 1. Then parts, in the first one there is a hint is also given. Okay, let me just write that here. This is the hint that helps us in carrying out the induction step. 5 square times 5 to the power 2k plus 7 plus 7 minus 5 square times 7. Okay, this is the hint to this one. Then in part C we have to prove that 5 divides 3 to the power 3n plus 1 plus 2 to the power n plus 1. Then in part D, 21 divides this plus this, and there is one more. In part E, we need to prove that 24 divides 2 times 7 to the power n plus 3 times 5 to the power n minus 5. Okay, so let us start with part A. And in each part we have to use induction to prove the result. Note that, so to start the induction we need a basis, and for that basis we would put n equal to 1. So if we do that, which is divisible by 8. That means this given statement is true for n equal to 1. Assume that 8 divides this for some integer, for some positive integer n. We now need to show that 8 also divides this expression when you replace n with n plus 1. So what happens when we take 5 to the power 2 times n plus 1 plus 7? This is equal to 5 to the power 2n times 5 square plus 7, and you can write this as what they have written here: 5 square times 5 to the power 2n plus 7. Originally, this one we already have, 5 square times 5 to the power 2n, but we have written 5 square times 7. Originally we had 7, so that means we have to subtract 5 square times 7 from 7, so plus 7 minus 5 square times 7. Now we are looking at divisibility by 8, right? So that means 24. So this is equal to, we can write one more step: 5 square times 5 to the power 2n plus 7, and if you take 7 common out, you get 1 minus 25, which is minus 24 times 7. Since 8 divides 5 to the power 2n plus 7. This is our induction hypothesis. And 8 also divides this second term, because 8 divides 24. We have 8 dividing this expression, which is nothing but this. Two times n plus 1 plus 7. This completes the induction. And you can extend this line by continuing like this. This completes the induction and proves that this is true. You write this for all positive integers n. I am not writing that part, okay, that is understood. So this completes the induction, and so the given relation is true for all positive integers n. Now we move to part B. Same. We first see what happens when we put n equal to 1. In this case, 16 minus 1, we get 15 itself. So that means 15 is divisible by 15. So our statement is true for n equal to 1. Assume this for some positive integer n. Now we'll look at this expression, putting n plus 1 in place of n. This becomes 2 to the power 4n times 2 to the power 4 minus 1, and this can be written as 2 to the power 4 times 2 to the power 4n minus 1. We have taken an extra 2 to the power 4 but with a minus sign. That means we have to compensate for that, we have to add 1 2 to the power 4. And this becomes equal to plus 15. Since this is divisible by 15, and this is in fact equal to 15, so the sum is divisible by 15. Without writing obvious things, we at once write this. That means ultimately, going back, this is divisible by 15. This completes the induction. Next, part C. So in part C, the divisor is 5. So when we put n equal to 1, we get what? 3 to the power 3 times 1 plus 1 plus 2 to the power 1 plus 1 equal to 3 to the power 4. 3, 9, 27, 81 plus 2 square is 4, 85, which is, okay, the power has come back. Let me just do something. Give me a moment. What I did is that I restarted the computer. I keep the computer running because I have already said that the part of the world where I am residing, it's not exactly quiet. So if there is no background hum, say, of the computer, the video may pick up some distant background noises, which is something is going on far away, but those sounds will be picked up. So that will be a disturbance. So that's what I did. Anyway, so which is divisible by so this is the basis of our induction. Assume that 5 divides this for some integer n greater than or equal to 1. Now we replace n with n plus 1. Now 3 to the power 3 times n plus 1 plus 1 plus 2 to the power n plus 2. That's what we get if we replace n with n plus 1 here. Okay, now this can be, the first term can be written as 3 to the power 3n plus 1 times 3 cube plus the second term is 2 times 2 to the power n plus 1. Okay. Now what we need is this 3 cube is there, and with this one we have 2. So in this case, okay, so let us write like this: 2 times 3 to the power 3n plus 1 plus 2 to the power n plus 1. Here we originally had 27 number of 3 to the power 3n plus 1. From among them we have taken only 2. So that means 25 are remaining. So plus 25 times 3 to the power 3n plus 1, because 25 plus 2 is 27 and this is 27, and here we originally had 2, so that we have taken common ground. Since 5 divides the first term, means this factor in the first term, and that is our induction hypothesis, and 5 also divides 25, so that means it divides the second term. We have 5 dividing their sum or their combination, which ultimately is nothing but this. So that means the given divisibility relation is true by induction for all n. This completes the induction. Then part D. In this one, if we put n equal to 1, we get if we put n equal to 1, then we get 16 plus 5, which is actually 21, which is divisible by 21. So that is the basis of our induction. Now assume that 21 divides 4 to the power n plus 1 plus 5 to the power 2n minus 1 for some integer n greater than or equal to 1. Now if we replace n by n plus 1, we will concentrate on this expression. Okay, now first of all, this becomes 4 times 4 to the power n plus 1 plus 5 to the power 2n minus 1 times 5 square, and the divisor is 21. Okay, 21 means this is 25. So if we take for, okay, yes, Note that you can write this sum as 4 times 4 to the power n plus 1 plus 5 to the power 2n minus 1. So out of that 25 number of 5 to the power 2n minus 1, we have taken 4 here. So the rest of the 21 are still there. So we are left with plus 21 times 5 to the power 2n minus 1. Since by the induction hypothesis this is divisible by 21, and 21 also divides 21 times this, we have 21 dividing this plus this, or in other words 21 dividing this. This completes the induction. One more is there, and in this last one we won't of course we will again be applying induction only, but we will need something extra. And that extra thing, I think we will prove that in the beginning of this solution itself. We first prove by induction that what was that extra bit? Oh yes, 4 divides 5 to the power n minus 5 for all positive integers n. Let us prove this first, and then this will itself be used in the original induction. Note that 4 divides 0, which is 5 to the power 1 minus 5. So that means our claim is true for n equal to 1, and this is the basis for our first induction. Now assume for some positive integer n, then five to the power n plus 1 minus 5 is clearly 5 times 5 to the power n minus 5, and that can be written as 4 times 5 to the power n plus 5 times 5 to the power n minus 5. 4 times this plus 1 is 5 times this. Now this part is divisible by 4 by our induction hypothesis, and this part obviously is divisible by 4. So without writing those details, which we can clearly see, which is, we directly write which is divisible by 4. This completes the induction. Okay, now with this result at our disposal, we start the actual induction to prove whatever we are given here. Note that I need ink. Now the basis for this induction is obtained by putting n equal to 1. So 2 times 7 to the power 1 plus 3 times 5 to the power 1 minus 5 is what? (14 plus 15 minus 5). 15 minus 5 is 10. 10 plus 14 is 24. So we get 24 itself. So which is divisible by 24. That means this statement is true for n equal to 1. Assume that 24 divides this number Now that we are solving this last part, we can wrap these things up. So assume that this is true for some positive integer n. Okay, now we have to see this expression when we have n plus 1 in place of n. Minus 5, and the way we will write this is this. This is equal to, it can be written in the middle, two times 7 to the power n plus 1 plus 3 times 5 to the power n plus 1 minus 5, and this can be written as 7 times 2 times 7 to the power n plus 3 times 5 to the power n minus 5 minus 6 times 5 to the power n minus 5. Let's see if it's true or not. 7 times 7 to the power n is 7 to the power n plus 1 times 2 is this term. Okay. Now what about 5 to the power n? Here you have 3 times 7, that means 21, minus 21 times 5 to the power n minus 6 times 5 to the power n. 21 minus 6 is 15. 15 times 5 to the power n. In that 15 you already have 5, 3 times 5. So 15 times 5 to the power n is the same as 3 times 5 to the power n plus 1. Okay. And what about the constant terms? Minus 35 plus 30 is minus 5. So this is okay, this calculation is okay. Since 24 divides this, that is our induction hypothesis, and by what we have proved in the previous paragraph, divides 5 to the power n minus 5. See, that's where it is used. So because of these things we have 24 dividing this. Five to the power n minus 5 by this divisibility relation is a multiple of 4. That times 6 is a multiple of 24. So that means 24 divides this. Or same thing, 24 divides this. Excuse me. Hence, by induction or by the principle of mathematical induction, 24 divides for all positive integers n, and this completes the entire solution. Next, exercise 5. Prove that for any integer a, one of the integers a plus 2 and a plus 4, one of them is divisible by 3, irrespective of what a is. And note that here a can be a negative integer also. It's not like a is not like n here. Here n is a positive integer, here a is any integer. So you cannot, you can, if you want, apply induction here, but that will not give you all the cases. And with induction you won't get anything fruitful. Instead, here you have to use that our Euclidean algorithm or division algorithm, which tells us that every integer a is one of these two forms, 3k plus 1 and 3k plus 2, depending on the remainder it leaves when you divide it by 3. Since let's start like this. We know that a is one of the, or rather a is of one of the forms (3k plus 1 and 3k plus 2), where k is some integer. If a is equal to 3k, then a itself is divisible by 3. If a is equal to 3k plus 1, then a plus 2 is divisible by 3, because then 3k plus 1 plus 2 will be 3k plus 3, so which is divisible by 3. And finally, if a is of the form 3k plus 2, then a plus 4 is divisible by 3, because in this case a plus 4 becomes 3k plus 6, again which is divisible by 3. So that's just it. You can take some specific value of a and see that this is true. Then, and note one more thing, that the fact that a is exactly of one of these forms does not depend on whether a is positive or negative or 0. This fact is about any integer a. The integer that we are dividing by 3, whether it is positive, negative or 0, it does not matter. The possible remainders are 0, 1 and 2. When the possible remainder is 0, a looks like this. If the remainder is 1, a looks like this, and when the remainder is 2, a looks like this. K itself may be positive, negative or 0. Okay, so that will take care of the cases of the signs of a. Then exercise 6. For an arbitrary integer a, verify the following. Part A. 2 divides a times a plus 1 and 3 divides a times a plus 1 times a plus 2. Okay. Part B. 3 divides a times 2a square plus 7. and there is a part C also. If A is odd, then 32 divides a square plus 3 times a square plus 7. Solution. So in part A, the first divisibility relation is rather easy. Since A is either even or odd, A times A plus 1 is always even, hence 2 divides A times A plus 1. What are we saying here? We are saying that A is either even or odd. As an integer, it is either even or odd, and this fact is just equivalent to the fact that A is either of the form 2k or it is of the form 2k plus 1. And where is this in turn coming from? This is coming from dividing A by 2. The possible remainders are 0 and 1. When the remainder is 0, A looks like this, and when the remainder is 1, A looks like this. And we call this type of integers even, and this type of integers are called odd. So when A is even, clearly this A times A plus 1 is also even, because A is divisible by 2, so this is also divisible by 2. And when A is odd, say A is of this form, then A plus 1 is even, because then A plus 1 is 2 times k plus 1, 2k plus 2. So then also this product is even, so it's always even. Or in other words, 2 always divides this. And to prove the second divisibility relation, where is it? This one. You proceed like this. That is, since A is of one of the forms 3k plus 1, 3k plus 2, we see that one of A plus 1 and A plus 2 is of the form 3k. Or if you find this somewhat confusing, let me write 3k prime. When A is of the form 3k, then of course A is also of the form 3k prime. K and k prime are the same. When A is of the form 3k plus 1, then A plus 2 is of the form 3k prime, because in that case it is 3 times k plus 1. And when A is of the form 3k plus 2, then A plus 1 is of the form 3k prime. And here again, A plus 1 is 3k plus 3, or 3 times k plus 1. So one of these three numbers is always divisible by 3. So their product is also divisible by 3. Hence, in fact, using this, extending these two observations, you should be able to see that the product of n number of consecutive integers is always divisible by n. Try to see that. Try to think of why that is true, and it follows from this type of reasoning. Okay, now part B. In part B we have to prove this. Again, we know that A is of one of the forms three k plus 1 or 3k plus 2. If A is 3k, then three divides A. Or let me write the final conclusion. In brackets we can write since 3 divides A. If A is equal to 3k plus 1, then what happens? Then we have to look at the other factor, the one other than A. And here we just expand this using A plus B whole square formula. 6k plus 1 plus 7 plus 12k plus 2 plus 7 is 9. And so, and this is divisible by 3 because this is 3 times 6k square plus 4k plus 3. So this part is divisible by 3, so this product is divisible by 3. Finally, if A is 3k plus 2, then k square plus 24k plus 15, and which is also divisible by 3 because 15 is divisible by 3, and so here also we have the divisibility, and that completes part B. Now in part C, it is given that A is odd. Since A is odd, we have A is equal to 2k plus 1 for some integer k. Now the expression is this. times 2k plus 1 whole square plus 7. Four k square plus 4k plus 1 plus 3 4 times 4k square plus again 4k plus 1 plus 7 is 8. And in this case we have to prove that this integer is divisible by 32. We can take 4 common out. Here also we can take 4 common out. So that means 16 times k square plus k plus 1 times k square plus k plus 2. Since by part A two divides this product, we have 32 dividing 16 times this times this, that is note that here this product is of the form a times a plus 1, where a is k square plus k plus 1. We have already seen that that is always even. So besides this 16, you can find a 2 here, because one of these integers will be even. The other will be odd, we don't bother about that. We will get another 2. So because of that, 16 times 2 will be 32. 32 times something, and that something is an integer. So this entire product is divisible by 32. That is, this is divisible by 32. So this completes the solution. Shall I solve one more? Let's just stop it here. It's because I had to switch off the computer because of the lightning, so I lost track of time. So I'm not sure how much time has elapsed since we started this video. So it may be that we are already running out of space. So let me just end it here itself. If you want to say something about these things, you can of course write in the comment section below. Today is 24th, so the next one will be 25, 26, on 27 on graph theory, and Gregory's abstract algebra solutions rigorous exercises. One upload of that will be there on Saturday as usual. So on Saturdays we will have rigorous abstract algebra. So that will be all for tonight. So see you in the next video. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.